Welcome to the solutions to the Regents Physics Circular Motion and Gravity problem set, problems number 8 through 11. Let's jump right in. Number 8, the moon and the earth are attracted to each other by gravitational force. Does the more massive earth attract the moon with a greater force than the moon attracts the earth? Explain. This explanation is discussed here by looking at Newton's universal law of gravitation and comparing the force of the earth on the moon to the force of the moon on the earth. Let's take a look at our force of the earth on the moon here done in red. Fg equals big G. It would be massive earth, massive moon, divided by the distance between the center of the earth to the center of the moon squared. And you can see we've labeled that in the diagram up here as R. Center of the earth to the center of the moon. We take that value and square it. If we calculate the force of gravitational attraction of the moon on the earth, that would be Fg equals big G, mass of the moon, mass of the earth over distance between the earth and the moon. Moon and the earth, however you want to look at it, squared. The point of this conversation is, if you look at these two equations, they're identical. It's just that the masses are in different orders, but because it's multiplication, and multiplication is commutative, then you'd end up with the same Fg value. And by the way, you may then also remember Newton's third law, that if the earth pulled on the moon would be pulling on the earth with an equal and opposite reaction force, and these two forces are equal to each other. We end up with a misconception that the earth pulls harder on the moon, and that's what makes the moon stay in a circular orbit around the earth. And while that's true, that the gravity is what keeps the moon traveling around the earth in its orbit, it's not because the earth pulls harder on the moon than the moon pulls on the earth. The two forces, as shown here, are equal. All right, let's go to number 9. If the earth were twice as massive but remained the same size, what would happen to the value of big G? Well, we got our universal gravitation equation here. Fg equals big G, m1, m2 over r squared. You can let the earth be m1, the object on the earth m2, and the distance between the center of the earth to the object would be the radius of the earth, and we would square that. If they want to double the size of the earth but have its radius stay the same size, what would happen to the value of big G? Big G is a constant. It's a universal gravitational constant, and so nothing would happen to it because it's a constant. On to number 10, similar question. If earth were twice as massive but remained the same size, what would happen to the value of little g? And here in this, we see Fg equals big G, mass of the earth, times mass of the object placed on the surface of the earth, divided by the radius of the earth squared. That would be the distance from the center of the earth to the center of the object, would be the radius of the earth. And we also see that another way to measure the force due to gravity is what we've traditionally done in here, because that's also weight, and so that would be mg. So here's your mass of your object times little g, the acceleration due to gravity on Earth. This is what they're asking you to find and compare here. Well, if these two are equal to each other, we can go ahead, and there's an MO term, mass of the object cancels. And so little g would be big G, mass of the earth over radius of the earth squared. And you can see that if we double the mass of the earth without changing the size of the earth, that would end up as a direct relationship between these two, and therefore the acceleration due to gravity on Earth would also double if we doubled the mass but the Earth remained the same size. Lastly, number 11, Charlie Brown has a mass of 70 kilograms and Lucy has a mass of 50 kilograms. Charlie Brown and Lucy are standing 20 meters apart. Lucy looks up and sees Charlie Brown. She feels an attraction. If the attraction is gravitational, find its size. Assume that Charlie Brown and Lucy can be replaced by spherical masses. To solve this, we start with Newton's universal law of gravitation. Fg equals big G m1 m2 over r squared. We make our substitutions. Big G off the reference table, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. M1 can be Charlie Brown's mass of 70 kilograms. M2 can be Lucy's mass of 50 kilograms. And we're told they're standing 20 meters apart. And don't forget to square that in the equation. Go ahead and do your calculation, and you should get 5.84 times 10 to the negative 10 newtons. This is very, very small, and so the attraction that Lucy feels is not gravitational. It must be, well, something else. All right, that'll do it for these problems 8 through 11. More to come on force due to gravity as we do number 12 together in class tomorrow.